Welcome to second session of sequential circuits. In today's session, we will go through details of the flip-flop that is the basic circuit which we studied and its further versions. So, the title you can consider for today's session is about flip-flops. So, for the last time now I will draw the internal diagram, henceforth there will not be any need. The internal diagram is like this, which I just repeat. The truth table which we had discussed, I write the old names and then new names given which we would be using. The truth table I again repeat. A, B, C, D. A, B, C, D. Then 0, 0, 0, 1, 1, 0, 1, 1. In that case, I will put it 0, 0, 0, 1, 1, 0, and here it can be anything. We discussed it yesterday. Now, what do? We decide to not allow, to ban this state which we call as forbidden. So, if this is a forbidden state, then instead of writing both combinations, what we write? It can be either, the meaning is same, it can be either 0 or 1 0, but what exactly it would be depends on what was the last state. So, once we write forbidden here, we can write last state. We can write last state here. Once we write last state here, so the names which are used globally are for this unit flip-flop. This is S, this is R, this is Q, and this is Q dash, Q bar, but we use Q dash which is proper name. So, the truth table is R, S, Q, Q bar or Q bar, or in our words Q dash, because it is normally equal to Q bar. Because this is forbidden, we can say it is Q bar equal to Q dash when it is the last state is, that is the last combination is a not allowed, banned or forbidden combination. So, this is very clear. R, S, Q, Q bar or Q dash. I think we use Q bar because we have now banned this, henceforth we will not be using this. So, we can say let us follow the global convention R, S, Q, Q bar, but if banned state is allowed, then Q is equal to Q bar equal to 0, because the names are given after banning this state. Names are given after banning this state, names are valid if this is forbidden, this last state description is valid if this is forbidden. Now, R and S normally this column and this column, so when this is 0 1 it is 1 0, so that it should look in the same sequence, we just interchange the writing of this column, meaning we are not changing. So, the globally known truth table of RS flip-flop or SR flip-flop, it is called as RS flip-flop, but while writing we write S first because Q comes first. Q bar, 0 0, last state, 0 1, 0 1. Why? Because we are just interchanging the columns. 1 0, 1 0, 1 1, it is 0 0, and as an indication of forbidden, we should put a cross indicating that it is not that it is impossible. Putting a red cross it is not allowed. It is possible but banned, not allowed, which we can say as forbidden. So now the truth table, this diagram we will not draw, this we will rub out. Rub out in the sense that we will not be showing any internal diagram henceforth. It is everything is assumed now, means that is known to us, and the diagram shown will be of the flip-flop of this type, wherein we show S on the top side, a block diagram, that entire cross coupled NOR gates are put in a square box, and then we show S and R and Q and Q bar. But remember that it is Q dash, that you should never forget. Some people show R on the top, but it is good convention. When S equal to 1, Q equal to 1. When R equal to 1, Q bar equal to 1, or when R equal to 1, Q equal to 0. And now the names we show inside. Why? Because when we use multiple flip-flops, in that case there is confusion of which pin of which flip-flop. So it is now very clear: S, R, Q, Q bar or Q dash. I again repeat, Q bar you should treat it as Q dash. So this is the flip-flop, this is the block diagram, this is the truth table. So this is now should have a permanent embossing on you. Permanent embossing means what? If you put this combination S equal to 0, R equal to 1, Q will be 0, Q bar will be 1. Now if you make R equal to 0, means if you keep S equal to 0 and R equal to 1, Q will become 0, Q bar will become 1. Now if from this state you just make a change, means you keep 0 as it is, and from this one you go to this 0, then inputs will be 0 0 and outputs will remain 0 1. Outputs will remain 0 1, right? So for 0, now this we have banned. So what we do is that we rub it out. In the exceptional situation we will take its use. So we rub it out so that only 3 input combinations I am allowing. I am not allowing 4th input combination. So if now out of these 3 input combinations, it's a sequential circuit now. So there are 3 input states, 4th is banned. For 3 input states, there are 2 output terminals now. So 2 output terminals will be having multiple combinations. What combinations it may have? Since I have banned 1 input state, the outputs will either be 0 1 or 1 0. Output will be either 0 1 or 1 0. Now for S equal to 0 and R equal to 1, I get a defined output as 0 1. For S equal to 1 and R equal to 0, I get defined output as 1 0. And now so these are 2 input combinations which have got a unique output combination for each of them. But for this input combination, both output combinations are possible. Both output combinations are possible. Now what output combination will be, that depends on how you have arrived at that state. That I will once again explain the concept of memory. So now we can draw it in a different format. So I draw SR states as 0 0. Blue are SR states, or I can write here again SR. I will draw it. on different side. In blue, I am writing different possible states for input. Once we have banned other state, then let us not worry about it, because that will unnecessarily confuse. So blue circle shows the possible combinations of SR as 0, 0 I have shown in the middle, 0, 1 on one end and 1, 0 on the other end. Now for output, there were also 3 states possible, but the input combination which was required to have 0, 0 state we have banned. So in this condition, the output combinations output states I am showing in red circle. These are the states for Q, Q bar. Remember, Q bar is always Q dash, but right now since we have banned the previous state, it is Q bar. So that is 0, 1 and 1, 0. Now, what is the situation? What is the correspondence? That correspondence I will show you by another color. So, if S is equal to 0 and R is equal to 1, irrespective of where you were earlier, there would be a fixed output state. Now, I will show you different examples, again by taking a day-to-day life example. So, state 0, 0 is input state 0, 0 is like a hostel room. State 0, 1 is like a study room, and state 1, 0 is like canteen. Input sequences define your location. Study room, you can say study room, hostel and canteen. Study room, hostel and canteen. Now, output states are 0, 1 and 1, 0. Those I will define as serious or studious, I can say. Studious is a very, what we can say, difficult word, and relaxed. So, output states are a studious state and relaxed state. Now, if we assume that a normal student, not extremely sincere, who will also study in canteen, and not extremely casual, who will gossip in study room. So, for a normal person, what will happen? If normal person is there in study room, what will be his state? He will be studious. So, in study room permits a student to be studious only. Study room does not permit a student to be in a relaxed state. So, for input combination in study room, you can't be relaxed. So, this is never permissible. Whenever you are in study room, you are studious. So, an input combination 0, 1 results into output combination 0, 1, no possibility of other output combination, sorry. In canteen, you would be relaxed. There is no question of studious in canteen. So, from canteen, if input combination is 1, 0, output state is 1, 0. In canteen, you are relaxed. Now, what I am showing again is this is impossible. I have deliberately drawn this thing, right? So, you can't be relaxed in study room. Similarly, you can't be studious in canteen. So there are 3 input combinations, 2 output combinations. Out of these 3 input combinations, 2 input combinations are such that they define you, they take you to a defined output state. They take you to a defined output state. There is no possibility of other output state. However, now the thing is very interesting, and I hope that with this simplified description, even if you decide not to understand, understanding will be imposed on you. Now in hostel, what you can be? In hostel, it is possible that you can study in hostel, you can relax in hostel. Now, it depends on what mood you were earlier. It depends on what mood you were earlier. So, if you were, so first let us first draw 2 things. So, from hostel, when you are in hostel, it is also possible, right? When you are in hostel, both output combinations are possible. For 0-0 input combination, either 0-1 can be output combination or even 1-0 can be output combination. Now, what we will discuss in detail now is when you are in hostel, and it is assumed that when I say canteen, it is everything except study room. Study room includes classroom and canteen includes playground, everything else, right? I hope it is very clear. So when you are in between, when you are at a place which allows multiple states, or when you are having an input combination which allows multiple output combination, then what exact output combination will be depends on when you were not in that deterministic state, where were you? I again repeat, or I will use the change in medium of instruction because that is too complex concept. I will use mother tongue, which is Marathi for majority of you, or I will use Hindi also if required, but I think Marathi is very well connected with Hindi, so you can understand. I again repeat, तुम्ही जेव्हा हॉस्टेलमध्ये असता तेव्हा सिरियस किंवा स्टुडियस असू शकता किंवा रिलॅक्स असू शकता. स्टडी रूममध्ये तुम्ही असाल तर तुम्ही सिरियसच असणार, स्टुडियसच असणार. कॅन्टीनमध्ये असाल तर रिलॅक्सच असणार. पण हॉस्टेलमध्ये दोन्ही असू शकता. मग जेव्हा दोन्ही म्हणजे स्टडी रूम हे डिफाइंड डिटर्मिनिस्टिक इनपुट कॉम्बिनेशन आहे, कॅन्टीन हे डिटर्मिनिस्टिक इनपुट कॉम्बिनेशन आहे आणि हॉस्टेल हे नॉन डिटर्मिनिस्टिक इनपुट कॉम्बिनेशन आहे. म्हणजे 0-1 ही डिटर्मिनिस्टिक इनपुट कॉम्बिनेशन, इनपुटला मी कॉम्बिनेशन म्हणतो, आउटपुटला मी स्टेट म्हणतो, म्हणजे कन्फ्युजन होणार नाही. 0-1 हे डिटर्मिनिस्टिक इनपुट कॉम्बिनेशन की जे 0-1 ह्या आउटपुट स्टेटला रिझल्ट स्टेट देतं. 1-0 हे दुसरं डिटर्मिनिस्टिक कॉम्बिनेशन की जे 1-0 हे आउटपुट स्टेट देतं आणि 0-0 हे मात्र नॉन डिटर्मिनिस्टिक आउटपुट इनपुट कॉम्बिनेशन आहे. नॉन डिटर्मिनिस्टिक इनपुट कॉम्बिनेशन म्हणजे की जे ह्यातली कुठली पण स्टेट देऊ शकतं. म्हणजे कुठली स्टेट देईल हे मी नुसत्या कॉम्बिनेशन वरून काढू शकत नाही. 1-0 इनपुट कॉम्बिनेशन असेल तर आधी काय होतं ह्याचा संबंध येत नाही, आउटपुट हे 1-0च येतं. 0-1 इनपुट कॉम्बिनेशन असेल तर आधी काय होतं याचा संबंध येत नाही, आउटपुट हे 0-1च येतं. पण 0-0 इनपुट कॉम्बिनेशन असेल तर दोन्ही आउटपुट कॉम्बिनेशन असू शकतात. त्यातलं नेमकं कुठलं ह्याच्याकरता ते जे नॉन डिटर्मिनिस्टिक इनपुट कॉम्बिनेशन आहे ते कुठून आलं, ते काही अगदी पहिल्यापासून हे खूप एक्स्ट्रीम केस झाली तर हॉस्टेलमध्ये काय तुम्ही जन्माला येत नाही, म्हणजे याचा अर्थ सांगायचा तात्पर्य असं की हॉस्टेलमध्ये तुम्ही येता ते कुठून तरी येता, एक तर कॅन्टीनमधून येता किंवा स्टडी रूममधून येता. सो नाव I will again use the conventional medium, English. So, when input combination is a non-deterministic input combination, then what will be the output state for that non-deterministic input combination is to be ascertained. Now, to trace it, you have to go back. You have to go back till that point when you were not in that combination. So, how many input combinations are there? 3 input combinations, 0, 1, 1, 0 and 0, 0. Out of these 3 input combinations, 2 input combinations are deterministic input combinations. They lead to a fixed output state, and 1 input combination is non-deterministic input combination which may lead to either of the output states. Now, to give answer to the question, see, both are allowed, but what it will be means, if a question is asked, the truth table permits both states, but both states can't remain simultaneously. You can choose open elective, means you can choose, but not both you can choose simultaneously. You have to choose one. Both, see, you have to choose fixed subject, there is no choice. For elective you have choice, but you have to choose once. You can't have both are allowed but not simultaneously. So both out. For a sequential circuit, when we say that for a given input combination multiple output states are possible, that doesn't mean that multiple output states remain simultaneously. It will remain in one of the states. It can remain in both, not at given time. Then what exact output state in which the system will remain is to be ascertained based on the history. How history is traced? When you are in hostel, prior to hostel means just you go back from where you have come. If you come from study room to hostel, it is expected that your state was 0, 1 and that state will continue. So, if you enter the hostel from study room, if you are entering the hostel from study room, that is input combination, a deterministic input combination. From a deterministic input combination, if you are leading to a non-deterministic input combination, then the state of the output which was 0, 1, that will remain. If you are if you are at 0, 0 from 0, 1, this I am drawing that this will lead to this input state, this output state. And if you are coming from canteen to hostel, you will be rejoicing the memories of gossip which you had in the canteen. So, when you are in canteen, you are in relaxed state. So, even if you come to hostel, your state of relaxation will continue. So, if input E was 1, 0, that time output was 1, 0. If you change input from 1, 0 to 0, 0, the output will continue. So, where were you? That is the memory. So, now I remove this. So, it clarifies the things. If you enter 0, 0 state from 0, 1, it will give this. If you enter 0, 0 state from 1, 0, it will give this. So, now if you start with 0, 1, output will be 0, 1. From 0, 1, if you make 0, 0, output will be 0, 1. Now, after 0, 0, if you make 1, 0, output will change to 1, 0. After 1, 0, again you change back to 0, 0, output will continue to be 1, 0. Right? So, I write the sequence again. Everything I will try my level best because the flip-flop is understood not in detail by many. So, I will write a sequence S and R and Q and Q dash. So, let us start with some defined sequence 1 0. What are the output? 1 0. From 1 0, if I make 0 0, what will happen? It will continue to be 1 0. From 0 0, I make 0 1. What will happen? It will become 0 1. From 0 0, from 0 1, I make 0 0. It would be continue to be 0 1. I hope now it should clarify. This is fixed. This is fixed. Now again, if I make 1 0, output would be 1 0. Anyway, so this is a fixed. For input to be 1 0, output will be 1 0 in any case, but you find that for input to be 0 0, you notice it here, you notice it here. So 0 0 is input, 1 0 is output. 0 0 is input, 0 1 is output. This is because you have come from this way. From 1 0, if you come to 0 0, outputs will continue to be 1 0. Then from 0 1, if you come to 1 0, from input 0 1, if you come to 1 0, so 0 0, outputs will continue to be 0 1. So output maintains last state when inputs are 0 0. Last state means what was the state when input was other than 0 0. For input other than 0 0, the output would be fixed, and for input 0 0, output would be last state. So now with this SR flip-flop idea to be very clear, so in the next lecture we will go for the remaining flip-flops and then counters. I think it is too much heavy dose, it is better to stop now.